Okay, so this is an example from the textbook, Randall Knight, chapter 26, number 62. And it's an example in which we have a 60-volt battery in series with two capacitors. One capacitor is a 12 microfarad capacitor, and the other capacitor has an unknown capacitance. Now, so reading the problem, it says a battery with an EMF of 60 volts is connected to the two capacitors shown. Afterward, the charge on capacitor 2 is 450 microcoulombs. What is the capacitance of capacitor 2? Okay, so in this problem, we're given a limited set of information. We know the EMF of the power supply, and we know we have two capacitors in series. First thing to do is to redraw our picture. So in redrawing our picture, I'm going to draw the battery as a source of EMF using the symbol Psi, and I'll just label that to be our 60 volts. I'm going to go ahead and specify that as to 2 sig figs because the sig fig rules of the book is I don't really follow when it comes to zeros. So I know they're going to want this to 2 sig figs. So I'm going to specify 2 significant figures with my decimal behind the 60. Also, with these two capacitors, they are wired in series. And labeling capacitor 1, we know capacitor 1 has a capacitance of C1, and C1 is given as 12 microfarads. Now, while we're at it, we know that after the battery is attached to the two capacitors will become fully charged. So I'll indicate the charges, the magnitude of the charge on each plate of the capacitor as Q1 and Q2. Now, one thing we should recognize, since these are capacitors in series, the charge on capacitor 1 is going to be the same as the charge on capacitor 2. So I'll just label that as Q1 equals Q2, and we'll just go ahead and call that Q. And another thing we should recognize, and this is just part of our problem-solving setup, so I'm not even really yet diving into what I need for the problem. I'm just making connections between all the different parts. So another thing that we should recognize is that these two capacitors in series can be replaced by a single equivalent capacitor. So I'll identify the single equivalent capacitor as C12. And C12, we know, is going to have a charge of Q12 for our equivalent capacitor. We should recognize and acknowledge that for capacitors in series, not only is the charge on their plates equal, but it's also the same as the charge of the equivalent capacitor. So I'll just call this Q. I'll just relabel it as Q12 for the charge of the equivalent capacitor. Useful bit of information there. Now, the problem is asking us to find the charge on capacitor 2. And it's also finding, or let me rephrase that. It gives us the charge on capacitor 2. The charge on capacitor 2 is 450 microcoulombs, but it's asking us to find the capacitance of capacitor 2. So let's see the pieces we have. Well, we know the capacitance of capacitor 1. We also happen to know the charge on capacitor 1 because it's the same as the charge on capacitor 2. We know the voltage of the power supply, the 60-volt power supply, and we know the relationship of valley, college is quaint. This relationship relates for us the potential difference of a capacitor, that capacitor's capacitance, and the charge on the capacitor. So I see that if we wanted to find the capacitance of capacitor 2, we would need to know its potential difference, we would need to know its capacitance, and we already know its charge. And I said we need to know the capacitance. That's what we're trying to find. So really, if we want to find the capacitance of capacitor 2, since we already know what its charge is, we're going to need to find the potential difference of capacitor 2. Now, one other thing I should label in our diagram are nodes. And nodes are points that connect two or more components. So essentially, in between each component, I'm going to put a node. I usually like to start with the negative terminal of the battery, and I usually will call that A. And then the positive terminal we'll call B. And then working around clockwise in the circuit between capacitors 1 and capacitor 2, I'll call this C. Now, we know that the potential difference of the power supply is, I'll just label it from A to B. The potential difference from A to B is equal to the potential difference of the power supply, 60 volts. That's when we go around our circuit counterclockwise through the battery. Now, if we go around, it must be early morning because I keep mixing my words. That would be the clockwise direction through the battery. The counterclockwise direction would take us through both capacitors. And that would also be a potential difference from A to B. In going through both capacitors, we would see that to get from A to B, we would have to go across capacitor 2. So that would be the potential difference from A to C. And then we would have to go across capacitor 1. That would be the potential difference from C to B. Now, we know that the potential difference from A to C, that's just a relabeling of the potential difference across capacitor 2. And the potential difference from C to B is just a relabeling of the potential difference across capacitor 1. Our goal is to, if we could find the potential difference across capacitor 2, then we'll be able to find the charge or the capacitance of capacitor 2. So to do that, we have the EMF of the battery. We don't know the potential difference of capacitor 1. But we do know, again, the relationship Valley College is quaint. If we rearrange that relationship, we would get the potential difference of capacitor 1 is equal to the ratio of the charge on capacitor 1 over the capacitance of capacitor 1. And let's see, we have some information here. We happen to know the charge on capacitor 1. That's given to us because since capacitor 1 is in series with capacitor 2, and since we know the charge on capacitor 2 is 450 microcoulombs, that must mean the charge on capacitor 1 is 450 microcoulombs being in series with capacitor 2. And we're also given the capacitance of capacitor 1 being 12 microfarads. So what that means is we know everything we need for the potential difference of capacitor 1. And since we know the potential difference of capacitor 1, we could then find the potential difference of capacitor 2 by rearranging the previous equation. The potential difference of capacitor 2 is equal to the EMF of our power supply minus the potential difference of capacitor 1. So this then is the potential difference of capacitor 2 is equal to the EMF minus the ratio of the charge on capacitor 1. And since we know what the charge is of capacitor 1, that it's equal to capacitor 2, I'm just going to call this Q2, just acknowledging that Q1 is equal to Q2, and that reduces our variables. And then this is over the capacitance of capacitor 1. So we're almost there. I'll just call this equation 1 right here. I'll call this equation 2 right here. And what we are going to do now is we are going to place equation 2 into equation 1. So this is the capacitance of capacitor 2, remember, is the charge on capacitor 2 over the potential difference of capacitor 2. So this is the charge on capacitor 2 over the EMF of the battery minus the ratio of the charge on capacitor 2 over C1. And we could plug in numbers right here, but I'm just going to, I have a fraction underneath a fraction. So I'm going to just get some common denominators and rearrange this. So I'm going to basically multiply the numerator and the denominator by the capacitance of capacitor 1. So that puts us in the numerator having the product of the charge on capacitor 2 over the capacitance of capacitor 1. And in the denominator, that gives us the EMF of the power supply times the capacitance of capacitor 1 minus the charge on capacitor 2. So this should allow us to determine the capacitance of capacitor 2. And right here, before I plug in numbers, we could just do a quick unit check to make sure our algebra is at least reasonable. So I see we're looking for units of capacitance. I know that the product of potential difference in capacitance is charge. So the unit of charge is the coulomb. This term represents a charge term. The units of that is the coulomb. Here we have a charge term. The units of that is the coulomb. So I see coulombs in the numerator cancels with coulombs in the denominator, leaving us with capacitance. So therefore the units work out. We can now plug in our values. So the charge on capacitor 2 is 450 microcoulombs times the capacitance of capacitor 1, which is 12 microfarads. This is over the product of 60 volts and the capacitance of capacitor 1, which is 12 microfarads. And this is minus the charge on capacitor 2, which is 450 microcoulombs. We already know the units will work out because of our unit check. So now I'm going to just plug this into my trusty calculator. In the numerator, I have 450 times 10 to the minus 6. And then, and I forgot to put my units there. That's 10 to the minus 6 coulombs. So let's insert the units there. Times 12 times 10 to the minus 6 farads. And this is divided by 60 volts times 12 microfarads minus 450 microcoulombs. And looking at everything, I think I entered everything correctly. So we end up with a capacitance of 2.0 times 10 to the minus 5th farads. And I think that we could say that that is the same as 20 microfarads. And now we have found the capacitance of capacitor 2. And essentially, once again, how we did that is we just made use of all of the information we knew with capacitors in series. We made an equivalent capacitor. And actually, we could have did this another way too. We could have just did it with using the reciprocal of the sum of the reciprocals to find the equivalent capacitance of capacitor C12, but I see that we didn't need to do that on this problem. We had enough information with the method we chose to find the equivalent capacitance.